Hello everyone, welcome to Computer Science E7. This is Lecture 3, Exposure. If you remember from last week, we started talking a little bit about exposure and introduced some of the, just talked a bit about light as well. And we talked about how light is electromagnetic radiation. Now it's the propagation of photons, where we can use measure of photons to determine brightness, but also it has this property of wavelength, and the length of the wave, or its wavelength, basically determines the colors that it has. Also, we as humans, our eyes capture these photons using a variety of cells within the eye, including rod cells and cone cells, where each actually has a separate response to light. And we talked about how cones are primarily used for detailed vision and color vision, whereas rods are better for night vision and for motion. And we even talked a little bit about the actual response of these cells to light itself. So we have three different types, so S, M, and L cone cells, referring to small, medium, or long wavelengths. And then we have this dashed line, which represents rods. And one of the things that's interesting about this that I didn't actually get to mention last time is that you'll notice that the rod sensitivity peaks at about the cyan wavelength, but it drops off to pretty much zero at a very pure red light. And this is very useful to us because if you are ever outside at night, or even in a very dark room or a very dark area at night, and you need to preserve your night vision, you can use red light to try to illuminate a portion of whatever it is that you want to look at. And because the rods are not stimulated at all by red light, particularly as it's very, very red, not just sort of a kind of red, but I mean very red light, then that means that it's not going to destroy your night vision. So your rod cells will still be sensitive to light without having readjusted your night vision to sort of daylight vision, for example, where you then are not able to see anything. So this is particularly useful if you need to if you are outside for a long time, maybe taking photos or just doing something, and you need to preserve your night vision for whatever reason. You can use a pure red light to do it. And why more automakers, for example, haven't picked up on this, particularly for dashboard lights and this sort of thing, is sort of beyond me. They love to have all these futuristic-looking dashboard lights that are, very blue and very white, and this very easily destroys our night vision. Which, though I, obviously haven't done any sort of scientific testing, it just sort of seems like it's a bad idea to destroy your night vision when you're driving around at night. But anyway, so we talked about the similarity of our eye to an actual SLR camera, and how there's some similarities in that light enters in basically through the front of our eye and is focused by a lens and is captured and picked up by sensors, or the cells, these rods and cone cells in the back of the eye, much like the same thing happens in an SLR camera. And we talked about how the different quantities of photons, the more photons you have, the brighter something is, and that a camera sensor or a camera's piece of film, if it's a film camera, is very sensitive to a very specific region of intensity, so such that if it's any darker, if it's any less intense than that, then it's just going to appear black, and if it's any more intense than that, then it's just going to appear white. And so there's this very limited range that we can actually take well-exposed photographs. And so there's usually something that we have to do in order to try to limit the amount of light, for example, so that we don't get overexposure like this, and try to limit the number of photons that actually reach the sensor itself. And this was the introduction to bring us into exposure, about how there's a variety of exposure controls that we have on the camera that allow potentially fewer photons to enter and to reach the sensor for us to measure it. And the first one that we talked about last week was shutter speed. And so since photons are what determines, the quantity of photons determines the brightness of whatever it is that you're looking at, if you double the number of photons, then you are effectively doubling the brightness. And we talked about how this was the concept of a stop in photography, so that whenever we had one stop difference in light, we had in either a double in the number of photons or a half in the number of photons, and therefore a doubling of intensity or a halving of it. And however, if you notice from this image here, even though we have actually captured twice as many photons in this one stop increase from the properly exposed photograph, it may not appear to us, like if we're just looking at it with our eye, to be twice as bright. That's because our eyes play tricks with us when it comes to color and intensity and a variety of these other things. But using shutter speed, we can actually use it to have a variety of effects. So for example, if we have a long shutter speed, we can capture motion with it, and we can smooth out motion that otherwise would be very, very still. However, on the opposite end of the spectrum, sometimes you actually want to capture still images and try to stop the motion as much as possible, particularly with sports. And of course, like with every rule, there is an exception to this one as well. And sometimes there are some sports where you may want a little bit of blurriness or a little bit of motion blur in the photo in order to capture a little bit of livelihood or a little bit of just some of what was going on in that particular scene. It's not very interesting in this particular photo if everything was absolutely still. Then it could just look like that car was just sitting there and there was nothing really going on. So, but mixing motion blur with having a very sharp subject can be tricky, because you have to keep one particular subject absolutely centered, or not centered, but absolutely still relative to the sensor itself. So as you can see, some of the numbering on this car is actually relatively sharp, and that's because as this car was moving, if you follow it with your camera lens, and basically track it, follow it as it's moving along, then it remains still relative to the sensor, and you don't get this motion blur. But what can happen if you don't take care to keep something very still, for example, if you have a long shutter speed without a tripod, for example, you will actually get a blurriness that can result in the image. And I'm sure many of you have seen, if not all of you, are familiar with motion blur as a problem. And so, so using shutter speed, we usually see numbers in the form of like 1/1000th of a second, 1/125th of a second, or 1/60th of a second, something like this. And don't get too confused about what is a shorter and what is a longer shutter speed. If it's a fraction like 1/60th of a second, that's a slower shutter speed than, say, 1/125th of a second. And the reason for that is that 1/60th of a second is actually a longer amount of time that it is open than 1/125th of a second. So just keep that in mind. And those two are actually about one stop away from each other, because they're each half or a doubling of the shutter speed, basically. So there's more than just the shutter speed that we can change in a camera. So though we can use shutter speed to try to get certain effects, we're usually limited by other features or limitations even of the camera and of physics itself that determine basically what shutter speed we can set. So as you can imagine, if I had taken this photo here, for example, and it was taken at 1/1000th of a second, and let's say I increased the exposure by one stop to 1/500th of a second. So that means that, okay, now it's open for a little bit longer. Maybe I'll get a little bit more motion blur, but at those speeds, maybe not. It'll be tough to tell. But what will happen to the photo itself if that's the only change I make? That's right, it becomes brighter, it becomes one stop brighter, and in certain aspects of this image, this may become very bad. So there's some fairly white regions in this photograph that if it's increased by one stop, the number of photons that are hitting the sensor may overwhelm it in a sense, and you may just get big white splotches, or it'll just, it'll look horribly overexposed in certain aspects or in certain regions of the photograph. This isn't going to happen, of course, throughout the entire photograph. For example, this black area down here will now appear a little bit more gray, but uniformly you will see an increase in brightness. So we have to be able to adjust some other settings on the camera to try to compensate for this. So maybe I did want a shutter speed of 1/500th of a second, but is there something else that I could do in order to achieve this? And so that brings us to the second setting that we can essentially set on a camera, or the ISO, or the sensitivity, if you want to think of it that way. Though the sensitivity is a bit of a misnomer in the digital world, and it's okay if you think about it like that for now, but as we'll see, especially a few lectures from now when we talk about digital cameras don't actually change their sensitivity. It's sort of a trick what they do in order to change the ISO. But anyway, if you're familiar with film, you might recognize some of these values. For example, ISO 100. If you had a film camera, you went to the store to buy some film and you bought ISO 100 film, you knew that you could really only use that film outdoors or in very bright, very sunny locations. Otherwise, there just would not be enough light in order to capture an image. For example, it would be very, very difficult to capture an image indoors unless you had a tripod and a very long exposure. Similarly, you could use a very high ISO, a very high sensitivity, ISO 1600, for example, which is pretty, well, it's very close to sort of the extremes of film sensitivity, of what you would buy. You could buy more, but this is kind of representative of how much you could actually buy and be able to use it somewhat frequently. So this higher ISO would allow you to have faster shutter speeds, so that you would then be able to take pictures indoors in darker areas, for example. And it sort of makes a little bit of intuitive sense as well, even if you're not familiar with this sort of give and take between ISO and shutter speed, that if you increase the sensitivity of something, then you'll be able to, if you're increasing the sensitivity to light, then things will appear to be brighter, maybe for the same shutter speed. And that's precisely what's going on. But just like shutter speed, we don't get this for free. We don't get this extra sensitivity in the camera without a cost. And the cost in this case is noise. Whether it's film noise or in digital cameras, digital noise, which you can see particularly in the black and gray regions here in the comparison of these two ISO images. And so as a result, you have to be able to balance each of these things when you're taking a photo. Do I want to sacrifice the cleanliness, so to speak, of the photo to be able to get a slightly faster shutter speed, or do I absolutely have to have a very fast shutter speed and the cleanest image possible? These are all things that we have to consider. So the range now of a digital camera, it really depends on the camera. As technology advances, usually the range increases, but pretty much on most any modern camera you'll see ISO 100 to 400, even maybe 800, 1600, 3200, 6400. It goes up and up and up, and now the most modern cameras actually have ridiculous ISOs, but I'll save my excitement about talking about that for just a minute. But usually when you set the camera to its fully automatic mode, usually it will try to automatically select an ISO for you. And as you can see in the difference between these two images, that's not always what you want. Sometimes you really want to have a very clean shot and be able to get as little noise as possible within it, so you'll want to override that particular automatic setting. And usually when the camera has an automatic setting such as this, it's just a subset of what that camera's capabilities are. So usually cameras that are capable of, say, ISO 100 to 1600 will only automatically select maybe ISO 100 to 400 or 100 to 800 or something like that. And so very much like shutter speed, this sensitivity or this ISO actually has, we rate it in terms of stops. But, and also very much like shutter speed, a doubling or a halving of the sensitivity will double or halve the sensitivity. So in other words, as we go from ISO 100 and we double that to say ISO 200, we are now twice as sensitive, for example. So now back here at this particular image, you'll see that I have, this was taken at 1/1000th of a second at ISO 400. So let's say that I increase the ISO to ISO 800. Now what this allows me to do is have one stop faster shutter speed at 1/2000th of a second, and it will be exposed the exact same way. Remember I had mentioned before that if I change to the shutter speed without changing any other exposure values, I'm going to change the amount of light that enters into the camera and therefore the exposure of the final image. But I can adjust two of these settings, for example, and be able to maintain the same exposure while getting different effects. So by increasing the shutter speed to 1/2000th of a second, for example, I'll now be able to freeze the motion a little bit better, even though if you look at it, it's already fairly well frozen, but maybe things are happening a little bit more quickly than what this shutter speed would allow, but at the cost of having a slightly higher amount of noise in the image. So as I double the sensitivity, this is doubling this, or this is allowing me, one stop additional shutter speed that I could gain back in speed, if that makes sense. So normally, especially in film jargon, whenever you would go to a store, for example, and buy ISO 1600 film, they'd always call it fast film. And this never made a lot of sense to me when I was a kid. Like, why would I buy a slow camera when I could have a fast camera? I didn't understand what the difference was. But the reason is that when you have more sensitivity, you can have a faster shutter speed for the same amount of light. And that's all that this differentiation between fast and slow film, or fast and slow sensitivity, means. And in fact, you'll see that this fast and slow differentiation actually applies to a lot of things. People use it to differentiate between lenses, for example. There's fast lenses and slow lenses, and there's a whole variety of things that this terminology applies to, and it's referring to specifically the shutter speed. Okay, so this particular example, if you're curious, actually comes from a compact camera from a few years ago, a Canon PowerShot SX100IS. And what I want you to pay attention to is the difference in the noise characteristics between this slide and the next one, which is representative of a digital SLR from the same era, from sort of the same technological generation. Okay, so if you pay particular attention to the ISO 1600 section, and especially the black or the gray region where you can see a lot of noise in particular, as I move to the next slide, you'll notice that it is markedly better. It's quite a bit decreased. And there's something to be said about the size of the camera, and may not apply to all things, but in photography, one thing is certainly true, and that size does matter. As things get a little bit bigger, things are easier in terms of the physics in order to capture some light. So there's other things going on as well, but for right now, if we break it down and simplify it to its constituent components, one of the major factors between why this ISO 1600 is much cleaner, much less noisy than the ISO 1600 of the compact camera, it deals with the size of the sensor in the camera itself. The larger sensor is able to capture more photons and is therefore able to be a bit more sensitive. So in this particular case, this camera is from a Canon 40D. So now we're one generation newer now at a 50D, but I think the noise characteristics haven't really changed much. Usually as technology progresses, the noise characteristics actually get better. And in fact, some companies, or I guess that's perhaps too general, but Canon specifically recently decreased the number of megapixels in one of their digital cameras, their compact camera lines that they announced recently, in an effort to combat noise and to get noise to be as low as possible in low light situations. And so while size certainly does play a factor, the age also plays a factor. Newer technology is generally a lot better at dealing with noise than older technology was. However, there is a physical limit, and we are actually quickly approaching that. Yes?
What exactly is happening with the size of the sensor that's causing the noise? I mean, what is it about the sensors, specifically that causes when light hits a larger sensor, you get less noise?
So just to repeat for the camera, so why is it, what exactly is happening, or why does a larger sensor have better noise characteristics? And we could go into a bit of detail, but you can think of it. Remember, when we're talking about the intensity of light, we said that we're quantizing or counting the actual number of photons. So the more number of photons that we have, the brighter something appears. And you can imagine that if you have a fixed amount of light, for example, in this room or outside with the sun, or more generally, you can think of this as rain that's falling from the sky. So if you have one bucket that's a certain size and you're collecting some rain, and you have right next to it a much larger bucket, you're collecting more raindrops into the larger bucket. And that's sort of the same thing that's going on. You're collecting more photons in the larger sensor, and therefore it doesn't have to work so hard to count them, if that makes sense. So there's a lot less error when it's counting those photons in these smaller buckets, so to speak, and it's just a lot easier for larger sensors to then count these photons.
So is the noise going to spill over light that's not able to be?
No, noise is not spillover light. There's a variety of reasons why we have noise. One of them is that it's the electronics inside the camera that are causing some noise. So better quality electronics will generate less noise, for example. The other is literally just an error in trying to count the number of photons that it's collected. So if you have, like, to go back to this bucket analogy that we're actually going to refer to many times throughout the semester, but if you have a smaller bucket and you have sort of an inaccurate ruler, then you're going to get some error in how you measure how much water you've collected, if that makes sense. So maybe you're doing it, I can very quickly make the analogy break down, but maybe you're doing it too quickly and you're just trying to, get a basic level or basic reading of it, and so you could somehow inaccurately count the amount of water in that bucket, then you're introducing some error into that measurement, and then that reveals itself in the end photo as noise within the photo itself. It's just the differentiation. It's miscounting somehow, or somewhere in the electronics it's adding additional noise to it. This is a complex subject. We actually talk about this in the digital camera lectures when we focus more specifically on sensors and why this happens, but that's just sort of a general overview.